So we have covered quite a lot of things in the case of algebraic topology so far. We have looked into quite a lot of new concepts using the new tools or the new language of algebraic topology. What we are going to do now is we are going to proceed further with the Maxwell equation. So when we go forward, we have to look into one more aspect that is missing in order to model the Maxwell equation, and the aspect is called as orientation. The idea of orientation has been pretty much discussed in the literatures. What I mean by literatures is engineering literature or physics literature quite narrowly. So what they talk about orientation is mostly about the orientation related to the inner space. When I say inner space, this might be something confusing to you. What does it mean by inner space? If there is inner space, are there other spaces, and how do we make sense of those other spaces? And these are the things that we are going to look into in today's lecture. So with that as a preamble, let's look at the topics for today's lecture. So what we have got is, we have got the idea of spatial orientations. The second one is, we are going to discuss about the primal and dual complexes, and the third one will be on the topic of time orientations, and finally we will come to the aspect of modeling Maxwell equations using all the things that we have learned so far. So with that being the motivation, I think we should be going quite directly into the topic of spatial orientation. So let's look at spatial orientation. So what I mean by spatial orientation is something quite broader than what is being discussed in literature so far. That's what I said before. Let me qualify what I said. So when I talk about, let's say, the orientation of a line, I might think about the orientation that is going from point P0 to P1. I might talk about an opposite orientation that is going from P1 to P0. Likewise, when I am talking about, let's say, an area, I can talk about an orientation that is going clockwise. Likewise, I can also talk about an orientation that is going anti-clockwise. The same way, we can talk about a kind of a volume. Let's say this is a tetrahedron. I can talk about outward pointing normals. Likewise, I can talk about the other side, which is the inward pointing normal. So this is the way we define orientations mostly in the literatures. So if somebody talks about orientation, they might talk about either right hand oriented or left hand oriented, or clockwise or anti-clockwise, point A to B or B to A, things of that sort. This is a very, very narrow idea of orientation, and there is something more to it than what we know of. And this is something the applied physicist or engineering community don't pay attention to, but it is known to theoretical physicists and also to a larger body of mathematicians. So we will look into the other aspect of orientation, which we call it as outer orientation. So what we have discussed so far, whether the point is coming internally or outward, which we discussed, whether it is going from A to B or B to A, we have also discussed. It's clockwise or anti-clockwise, whether it is going out or coming in, whatever it is. So these are all the kind of orientation that we talked about so far. We call them as inner orientation. So inner orientation to a larger extent can be understood because it is almost on the same dimension or the same space of the body of the object itself. So when we talk about a line, it is along the line. When we are talking about surface, it's along the surface. When we are talking about the volume, it's internally in the volume. The volume we talk about a clockwise rotation or anti-clockwise rotation. So this is a curl or divergence, things of sort. We are talking about whatever is happening internally to the object. But this is very clear in the case of a volume. When we talk about divergence, we are talking about the outer orientation, whereas when we are talking about the rotation on the surface, we are talking about the inner orientation. Similarly, for a surface, the outer orientation is the direction in which it actually, the flux is going in or going out, whether if it is going in or going out. So it's the same surface, but its outer orientation is outside the surface body itself. So in other words, in the case of the inner orientation, you are along the surface, whereas in the outer orientation you are outside of that embedding space. So I have to tell you something that you have to pay attention to before making a conclusion on inner and outer orientation. That is something called as the embedding space itself. So what I mean by embedding space is nothing but if I am going to be in a two-dimensional model, if I am in a two-dimensional model, all I have got is I have got a point, I have got a line, and I have got a surface, and these are the inner oriented objects with inner orientation. So here I can talk about both points coming internally or a point where it's going outward. So it could be inward pointing arrow or outward pointing arrow, both are allowed. Similarly, in the case of a line, it could be going in this direction or going in the opposite direction. So for the sake of simplicity, I am going to only consider one direction. Likewise, I am going to consider only the clockwise direction. So if that being the case, what are the objects that are in the outer oriented space? For a point, it will be a surface. For a line, it will be a line itself. For a surface, it will be a point. But this line and this line, they have two different things. Here the line has orientation that is along the line, whereas here the orientation will be about the line. So the line will provide me the axis, and the orientation could be clockwise or anti-clockwise depending on the option which we are choosing. Similarly, in the case of a surface, it could be a thing that is diverging, or so it could be something coming in or going out. For the point, it could be the rotation about the surface in this direction or in the other direction. So when you see in the two-dimensional space, the inner oriented object has a counterpart. In a two-dimensional case, the counterpart of a point is going to be a surface, the counterpart of a line is going to be a line itself, the counterpart of a surface is going to be a point. So the point will become surface, the line will become line itself, and the surface will become a point. Of course, we are talking about orientation that are outer, that does not fall into the object itself. In the case of a surface, we are not talking about orientation along the surface, but going outside or inside. So that is why we call it outer orientation. So it is important to know in 2 dimension that there is a counterpart for each of these objects. So let us take now the case of a 3 dimension. So what is important to know is, in the 2 dimensional case, we had the point associated to a surface, a line associated to a line in the dual space or the outer oriented space, and the surface has a point. So let us look what happens in the 3 dimensional case. So likewise, we have a point, we have line, we have a triangle, surface, and we have a volume. For the sake of simplicity, I am assuming only one of those 2 options, like the point is, the lines are going away from the point. Likewise, I am choosing a direction that is going from left to right. Likewise, I am choosing the orientation that is clockwise. Likewise, I am thinking about a curl that is internally oriented. So it is on the inside of the volume, and the curl direction is, let us say, in the clockwise direction. So now these are the inner orientation. What we are going to do is, we are going to see the outer oriented space for these objects. What we are going to see is, for the point it will be the volume, for the line it will be a surface, for the surface it is going to be a line, and for the volume it is going to be a point. What you are going to notice is, in the case of the point here, this is going outside, and now what you are going to have here is divergence that is going to happen along this volume, and in the case of the surface, it is going to be a line that is piercing through the surface, and we are going to talk about the orientation along this line that sits on this surface, and in the case of the surface, it is going to be a line where the orientation of the line is given in one direction. So what we are interested is in the direction that is pointing here, and for the point it is going to be the curl. So as you compare the 2 dimensional case here, the point's dual is a surface, whereas in the case of the 3 dimension, the point's dual is a volume, not a surface. So depending on the dimension, the dual space is going to vary. So if you are in a 2 dimensional space, the dual space of the point is going to be a surface, whereas in the 3 dimensional space it is going to be the volume. In other words, what is important to know is, the primal space is fixed. A point will always be a point, a line will always be a line, the surface will always be a surface, and a volume will be always a volume in the primal space, in the inner oriented space. I use the word primal, an inner oriented space, in a manner that is similar. It can be also a dual space, but what I am talking about is, a primal space is a space where the definition of the field variables are associated, but let us look at it at a later stage. But what is important for you to know is, the inner space is going to be constant whether you are in a 2 dimension or a 3 dimension or any dimension. For most of the practical applications, you are going to be within the 3 dimensional space. So regardless of whether we are in 2 dimension or a 3 dimension, the point is going to be a point, the line is going to be the line, and the surface is going to be a surface, and a volume is going to be a volume, and the orientations are going to be also along the object itself. That is why we call it inner orientation. The outer orientation is going to be the dependent on the embedding space. If you are going to be in a 2 dimensional problem, it is going to be like the way we discussed. If you are going to be in the 3 dimensional problem, it is going to be the way we discussed. So with that as an introduction, let us look at what we have got for the summary for all the spaces. I think we have seen in the case of a 2 dimension, which is here, the point will be a surface, will be the outer orientation, line will be given by the line, surface will be given by the point, volume will be given, not defined here because in 2 dimension there is no concept of a volume, whereas in the 3 dimension you have got all the full set. The point will be the outer orientation for the point will be a volume, the outer orientation of a line will be a surface, surface will be a line, and volume will be a point. So far we have differentiated between the 2 different kinds of spaces. Now we are going to call them either primal or dual. I have already used the word primal or dual while describing the spaces, but let us see in detail what this means from the more topological point of view. So we have got the primal dual complex. The primal and dual complex are the 2 types of oriented complexes. If you say my orientations are going to be within the object, in other words inner orientation, I call it primal. So look at this example where you have got let us say this is a kind of a, these are the points we have got, in other words the 0 simplexes. What we are interested to know is if we call this one as our primal complex, what is going to be the dual complex? The dual complex is going to be as shown here. Let me draw it in black. So it will have the points which are so these points could be either the circumcenter of this triangle or it could be the barycenter. So if it is a barycenter, it will look more symmetrical. Let me draw it using the barycenter. And assuming that these are the node points like before, and we are interested in the barycenters. Let us say these are the barycenters. So what will happen is we are talking about barycenter to the face center. So it will be the line that is connecting the barycenter to the face center or the edge center. In 2 dimension we are talking about edge center. So we have got now, if we call this one as P, these points will be P tilde. The tilde is just to show that they are the dual coordinate, and that is what you have got in this slide. If you can see this slide, what you have got is these are the barycentric points which are P tilde, they are the dual coordinate of this surface. Remember we said the dual of the surface in 2 dimension will be a point. So we have the surface here, the dual of the surface will be this point. Remember we also said the dual of the line will be a line itself. So the dual of this line, this edge will be this edge, and remember that we had the dual of the point will be a surface. So if you consider this central point, the central node as a point, the dual of that point will be the entire thing. In other words, we have now got simplex that will be more formally called as dual and primal simplex. So let me make this more clear. This is also a point. So you have a point P. So the dual of this point is this surface. So this surface here is what we call here, this surface is this thing. So with this we have covered pretty much the concept of spatial orientation. In the next module we will cover what we mean by time orientation and then directly take you to the Maxwell equation. Thank you.